Granted. I just got them this morning since I wasn't here Friday, and I don't drive back up here on Saturday, so I don't have your test for you today. So I should have those for you guys on Wednesday. Also, don't forget Thursday and Friday we're not here. You have looked ahead and noticed that, huh? You're right. You probably won't have any homework tonight. Actually, there may be a little bit of homework, but you're definitely not going to have a very long assignment tonight because we're not going to get through everything today. So we'll be finishing up section 8.2 on Wednesday. So unlike how things have always landed where Fridays have been our good day off, it's going to be Monday being more of the day off, and Wednesday you'll get to have homework over your Easter break. So, yes. I do want the extended problems. So let me go ahead and grab those first. So, Chapter 8. Okay, so with Chapter 7, we went through and did the confidence intervals of, we were like 95% confident that, and we did it for proportions, we did it for the mean when we knew the standard deviation of the population, the mean when we didn't know the standard deviation of the population, and then for standard deviation and variance. And now we're going to do this hypothesis testing, and we're going to go through the exact same process of, we're going to do a hypothesis test for the proportion, a hypothesis test for the mean when we know the standard deviation of the population, the hypothesis test for the mean when we don't know the standard deviation of the population, the hypothesis test of standard deviation and variance. So the order of the way these chapters go is going to feel very similar to what we were doing in Chapter 7. Other than now we're testing different hypotheses instead of finding our different confidence intervals. And so we're doing something different with it, but it's still that same process that we're doing things with, and very familiar types of formulas that we're going to be looking at, whether we'll use the z-scores, the t-scores, or the chi-squared values. And so we'll be using the similar kind of things as we go through it. So kind of reviewing where we have been. Chapters 2 and 3, we use descriptive statistics when we summarize data using tools such as graphs and statistics, such as the mean and standard deviation. So before, we were just describing the sample data that we had. Methods of inferential statistics use sample data to make an inference or conclusion about the population. And so chapters 2 and 3, we were describing what we had. Chapters 7 and 8, we are inferring things about the population. So in Chapter 7, we were taking our sample and trying to say that we are so confident that we think that the mean is going to be between these different values. And so we were inferring what we knew about the entire population. Chapter 8 is going to be more of the inferential statistics. In Chapter 7, we presented methods for estimating the population parameter with a confidence interval. This chapter, we present the method of hypothesis testing. In statistics, a hypothesis is a claim or statement about a property of the entire population. And so when we're trying to make a hypothesis, I might claim that I think 60% of NCMC students are females. So I've made a hypothesis of what I think about the proportion of females at NCMC. We might have a claim that we think that the mean age of students is over 25. And so that would be my hypothesis. It would be my claim where I'm giving information about what I think is true about the entire population. Now, once I make my claim, now I got to figure out what to do with that. How can I decide if my claim is anywhere near right or if I'm really way off base? And that's what this is looking at. Your hypothesis test or test of significance is a standard procedure for testing a claim about the population. So I might have my little sample, and I would need a sample to be able to use this, but taking my sample and using it to make some sort of test to see if what I'm claiming to be true is going to sound accurate or not. So examples of hypotheses that can be tested. The Genetics and IV Institute claims that its XORT method allows couples to increase the probability of having a baby girl. So if I'm increasing the probability of having a girl, then I'm saying the proportion of girls is going to be more than 0.5. And so that could be my claim that I could have something on. A newspaper headline makes the claim that most workers get their jobs through networking. Again, most would be claiming that it's more than half that you're going to be doing this. And so I can turn that into a hypothesis to be able to do my test on. Medical researchers claim that when people with colds are treated with echinacea, the treatments have no effect. And so then trying to claim that the proportion would be the same as what it would have been before. And so looking at those types of things are ways that I can take a claim and turn that into a hypothesis test. Caution, when conducting hypothesis tests as described in this chapter and in the following chapters, instead of jumping directly to procedures and calculations, be sure to consider the context of the data, the source of the data, and the sampling method used to obtain the sample data. So don't just jump right in and say, oh, I've got some information, let me just start using my tools that I have. We've got to make sure that we've got good information first before we start doing anything else with it. So that's kind of giving us a quick general overview of where we're going. And like I said, we're going to do these basic hypothesis tests for each of these different types of things. So our basics of hypothesis testing. First of all, we will rely on our rare event rule for inferential statistics. Let me get your homework and stuff too. Rare event rule, if under a given assumption, the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not correct. So this is something that we've already used and talked about several other times. If we're looking at something that, if we're trying to calculate things out and the probability that it would happen is a very small chance that it would happen like that just with the assumptions that I've made, then I've probably made some wrong assumptions. So if I'm claiming that the proportion of girls on campus is more than 60%, then the probability that I would find a sample of 50 people and having all 50 of them being male, probably not likely to happen if my proportion of girls is 60%, around 60%. And so the assumption that that proportion was 60% or more was probably wrong. And so the probability of those kind of things, and it wouldn't even have to be quite that extreme. Even if I was talking about the proportion being 60%, and I get a sample of 50 students and 40 out of the 50 are male. Well, if that's good, if it's a good, simple, random sample, then that's probably very unlikely to have happened just out of chance if the true proportion of females was 60% and the proportion of males was only 40%. We'd expect those to be in reverse from what we were looking at. And so we always have to go back, and we usually still use that 5% as being our cutoff that we generally use unless we state otherwise within the problem. So our components of a formal hypothesis test. First of all, we have to have the null hypothesis. And again, just like we did back in Chapter 7, this first section takes a long time to go through everything because we're really looking at all of the basics of what it means. And then, and so this is just giving us a generalization of everything. And then we'll, in Section 3, go through and test the hypothesis about a proportion and actually go through each one of these. But there's a lot of terminology to really talk about in this section. The null hypothesis, which is denoted by H naught, is a statement that the value of a population parameter, such as the proportion, mean, or standard deviation, is equal to some claimed value. The null hypothesis is always that it's equal to something. I'm going to make the assumption that it equals that value. So even if I'm trying to claim that the proportion of females is greater than 60%, my null hypothesis would still be that P is equal to the 0.6. Your null hypothesis is always equals. And that is going to be an extremely important part of looking at things. And this can be for a proportion, mean, standard deviation. Each of those are going to be coming back to setting these kind of things up as we do it. Questions there? The null hypothesis is always what we are testing. So once we come to our conclusion, we will be making a conclusion about our null hypothesis. And so we will be very careful about the way we word our conclusions, because it's not testing directly what we claim to be true. We're not directly testing our original claim of our hypothesis. We are always testing that null hypothesis. We're always testing that fact that it's going to be equal. We will either reject the null hypothesis or we will fail to reject the null hypothesis. Notice we don't get to say the words, we support the null hypothesis. We're not going to get to make a claim about that null hypothesis has to be true. We're either rejecting the null hypothesis or we're failing to reject that null hypothesis. And we'll look at those as we go, exactly what that's talking about. Questions there? Now, we've got the null hypothesis. The other thing is the alternative hypothesis. The alternative hypothesis can either be listed as H sub 1, H sub lowercase a, or H sub capital A. I think the book does H sub 1. I always have to stop and remember because the book does H sub 1. When I was taking my upper level stats class, they were using the H sub A. So you'll probably see me do both. I'll try to keep it with H sub 1 so it looks like what the book does. So the book's using the H sub 1 is what we're talking about with the alternative hypothesis, is the statement that the parameter has a value that somehow differs from the null hypothesis. Your alternative hypothesis, make sure I'm not going to write, yep. Alternative hypothesis will either say that it's not equal, it's less than, or it's greater than. So when I was claiming that the proportion of females was more than 60%, then I would say that P is greater than that 0.60 would be my alternative hypothesis. I might be saying that the proportion, let's go with the mean age. The mean age, if I was claiming the mean age of students was more than 25. Well, if I was claiming that the mean age was more than 25, then my null hypothesis is that the mean was equal to 25. My alternative would be that the mean was greater than 25. The alternative does not include the equals. And that is a huge piece to pay attention to when you're looking at the alternative. It will never say that it's going to equal some value. If I originally claimed that the standard deviation was equaling 0.23, well, then that would be my null hypothesis. My alternative hypothesis would be that it does not equal the 0.23. So if I'm claiming it to be equal to, then when you're trying to find that alternative, it's whatever one does not include the equals between what you claim and when the claim is false. We'll kind of walk through a couple of those here in just a little bit. So there's different ways of expressing these, but you're going to be using, when you're doing that alternative, it does not include the equals is a key thing to remember. So if we look at page 396, it kind of steps us through how to write your hypothesis. So first of all, you have to identify your specific claim or hypothesis to be test. Express that in symbolic form. You will give the symbolic form that must be true when the original claim is false. Using the two symbolic expressions obtained so far, identify the null hypothesis, which is H0, which is always where it's equal, and the alternative hypothesis, H1. H1 is the symbolic expression that does not contain equality. So H0 is the symbolic expression that the parameter equals the fixed value being considered. The original claim may or may not be one of the above two symbolic expressions. So when we're looking at things, if I was to claim, actually let me just, well, let's see. Let's say I'm going to be claiming that the proportion of students that live in Trenton is less than or equal to 1/4. So if I'm claiming that the proportion of NCMC students that live in that grew up in Trenton is less than or equal to 1/4. Well, if that's my original claim, if that claim is false, how would I write that? If it's not less than or equal, then it has to be greater than. So when we're trying to figure out what our alternative is, we have to think about what the original claim is, and if that was not true, how I would write that. And so we have to put that into symbolic form. And do pay attention, and I will look for whether this is talking about proportion, mean, or standard deviation. And these are going to be population proportions, population standard deviation, and population mean that we're looking at. So now from those, what is, first of all, my alternative hypothesis? Alternative hypothesis is always where it's equal, so it would look like what? Okay, P is equal to 1/4. That's going to be a pretty straightforward one when you're trying to find the null hypothesis, because the null hypothesis is always where it equals whatever the value is that you're working with. My alternative hypothesis is which one of these two does not include equals. It's got to be where it's false this time. And so it's going to have that the P is greater than 1/4. And so it's whichever one of these two does not include the equals. Now, my original claim is that the proportion is less than or equal to 1/4. This time, the claim is not in either one of these. It's not in my null, and it's not in my alternative. What we're always going to be testing is the null hypothesis. We're testing the fact that it equals the 1/4. And we'll be able to make a statement based off what comes from that, is what we're going to be using. But in this case, that alternative hypothesis is just the greater than. Now, on the other hand, let's say I was to, let's say that I claimed that the mean age of students is, let me write it down this way. If I was to claim that the mean age of students was equal to 25 years old. If I'm claiming that the mean age of students is 25 years old, what would be the, actually, I'm going to give you guys a second. Figure out what's false. Figure out your null and your alternative. Oh, I guess I got some examples of those coming up here in just a second, too. So if I'm claiming that the mean age is 25, if that's false, what will we have? It's what? Does it have to be greater than? Okay, it could also be less than. So not equal to would be the one we're going to want to go with. Because it could be either greater than or it could be less than. We just know it's not 25. So then my null hypothesis is what? Okay, null is always where it equals. So this is that the mean equals 25. Which one of these two does not include the null, or does not include equals? Sorry, I'm saying things wrong. Okay, is that not equal to the 25? Questions there? Okay, let's look at a couple other examples. If we look at number 10 on page 409. On number 10, the proportion of people aged 18 to 25 who currently use illicit drugs is equal to 0.20 or 20%. If I want to write my null and my alternative, first of all, what symbol am I using? Am I using mu, p, or sigma? Okay, I'm using p because it's talking about a proportion. So my original claim is what? So I'm going to give you guys a moment to figure out what your null and your alternative would be. And I guess I should keep my 0 because it's significant in this one. So if this is false, it'd be saying what? Okay, P is not equal to 0.2. So my null is what? P equals 0.2. And my alternative? Okay, P is not equal to the 0.2. Because your alternative never includes the equals, your null is always equal. If we look at number 12, the majority of college students have credit cards. Sarah wants to go with the claim is that P is greater than 0.5. Do you guys agree or disagree? Give me a thumbs up if you think that's right. Give me a thumbs down if you think that's wrong. If I'm trying to claim that the majority is. Okay, majority means it's got to be more than half. So if it equals half, half is not the majority. So it's got to be more than half to be the majority. So what would be making this, if it was false, what would I have? Okay, be less than or equal to that 0.5. And so now what is my null? Okay, null is always equal. So what's my alternative? Okay, that P is greater than 0.5. Most of our claims, unless I'm claiming that it equals, most of my claims are either going to be greater than or less than. Usually I don't claim that it's greater than or equal to, but occasionally you run into those. So you've got to really read through what it is it's saying from the original claim to figure out what your null and your alternative hypothesis are going to be. Questions? Caitlin, question? This piece? It won't always be that case. It's whichever one of these two does not include the equals. So in this case, the claim itself did not include the equals, so that's why we went with the claim. And that's the reason why I wanted to make sure I did some of both. Because honestly, in your homework, you're going to get used to most of the time it's your claim that becomes your alternative hypothesis, but occasionally you get a strange one thrown in there that includes the equal as part of your claim. Okay, other questions? And I'm glad you asked because I wanted you guys to catch that difference. Any other questions there? Now, once I have what it is I have as my original claim, what is my null hypothesis, what is my alternative hypothesis, now I got to figure out how do I decide is my original hypothesis true or false. The test statistic is what we're going to use to help us with that. And we were using our test statistic as we were doing our confidence intervals. We were kind of looking at what those. We were looking at those special spots, or critical values, I guess, what we use here. Our test statistic is a little different. That's the value used in making a decision about the null hypothesis, and is found by converting the sample statistic to a score with the assumption that the null hypothesis is true. And this is the key piece, is we are going to assume that the null hypothesis is true. Assuming that I know that the proportion of girls on campus is 60%, then based off that assumption, what would be my test statistic? If I end up getting my test statistic that has a high probability of happening, then I can't decide whether I can reject or I'll have to accept my original hypothesis. But if I get a test statistic that's way off with a very small probability, then that's when I get to reject my null hypothesis. And so your test statistic is calculated, and now our test statistic will either be our z-score, our t-score, or our chi-squared score for the ones that we're doing this semester. And so we'll figure out what those are using the assumption that the null hypothesis is true. And that is that key piece that we're using in this. So our test statistics that we will use. If I'm finding the test statistic for a proportion, then to find my z-score, it's the difference between my sample statistic, or my sample proportion and my population proportion, divided by the square root of PQ over N. Should look very similar to what we've already done when we were calculating our z-scores. If we're doing the test statistic for a mean, if I know the population standard deviation, I'm finding a z-score. If I don't know the population standard deviation, all I know is the sample standard deviation, I'm calculating out the t-score. If I'm doing it for a chi-squared distribution, for a standard deviation or a variance, I'm finding my chi-squared score. And so all of these are things that we've already used, and I think if I'm remembering right, they're the exact same formulas that we were looking at. I guess they're rearranging these formulas that we looked at from Chapter 7. So on Chapter 7, when I'm finding my margin of error was that difference between my sample proportion and my population proportion. If I rearrange that and solved for z instead of e, then we're going to come up with that very top one. And so it's just rearranging these same things that we used for our confidence intervals in Chapter 7, we're now using in Chapter 8. One other thing I want to mention. So these are the formulas for Chapter 7. In Chapter 7, we had confidence intervals and sample sizes. It jumps to Chapter 9 next because Chapter 8's on the next page. So Chapter 8 didn't have as many things. So your test statistics for one population is up here at the top of this next page. And so we've got finding the z-score for the proportion, for the mean when we know the standard deviation, when we don't know the standard deviation of the population, and our chi-square distribution. Also, if you wouldn't mind just checking this now while I'm remembering it, make sure on your little forms, your pages that you guys use as a reference guide, your chi-square distribution is correct. Because their original one wasn't. I think if you've got one of my printed copies, I'm pretty sure I got it fixed. But on chi-squared, it needs to be divided by the sigma squared. Okay. So if you had the original paperwork before instead of getting a copy from me, it might not have been fixed. So I want to make sure that gets corrected on there, and I'll hopefully remember to mention that again when we get to that section. But these are the different test statistics we're going to use. So if I want to find the test statistic, if the claim is that the proportion is 0.25 from a sample of 580 when the sample proportion is 0.262. First question, which one of these formulas am I using? Okay, I'm using the very top one. I'm dealing with a proportion. And so if I'm doing the proportion, I'm using the fact that z is p hat minus p over the square root of pq over n. Out of all those, everything's given to you except for q. What is q? Okay, it's the 1 minus p, which is what, Nathan? No. Sorry, I thought you were the right one. 0.75. Why is q 0.75? Okay, the population proportion is 0.25. That's what I'm claiming to state. I'm stating that I think that the population proportion is 0.25. So now if I'm claiming this, then my null hypothesis, I guess I should have written that out. My null hypothesis is that p is 0.25, which what's my alternative in this case? If I'm claiming it's 0.25, then it's going to be that it's not 0.25. Go ahead and plug your numbers in and find your sample statistic. So find z. Rounding rule is going to go to the same place value as our z-scores, which has been 2 decibels. Should be getting into 0.67 then. So if you're not getting 0.67, let me know. Are you getting it? So as you're putting things into the calculator, you can either do it piece by piece by piece, or you can just plug it all into the calculator at once. One thing that you might turn out thinking is a little useful as you do some of these is, especially if you're putting things in, because I know Sarah was saying she had a little bit different answer because of the rounding error. If you're finding like this, the denominator first, one thing you could do, if I did the square root of the 0.25 times the 0.75 divided by 580, and so when we get to this, if you just round it to 0.018, you kind of end up with a different answer in the very end. One thing you can do is either just use the answer part, or if you hit store, which is right above the on, and then you can tell it where to put it. So if I did alpha and A, so alpha is the green key and A is right below it, what that'll do is it'll store that into letter A, and so anytime I use A after that, I could put it into the middle of any other problem. And so then I could just do the, what was it, 0.262 minus the 0.25, and then I can divide by alpha A, and it would take that answer from before. So if you're ever thinking you need to store it somewhere else because you're in the middle of a problem and you don't want to just write down and round to have a rounding error, store is an option that you can do. You can also just use second answer sometimes to be able to use that in the middle of stuff too, where your answer, A and S, is right above your negative sign. Okay, questions getting the answer of 0.67 on that one? Now, what that does is that creates my test statistic, breaks it into where is my critical regions. The critical region or rejection region is the set of all values of the test statistic that cause us to reject the null hypothesis. So when we're doing things, we will have what our significance level needs to be so that we know where is that region that we want to accept and where's our region that we want to, I guess I can't say accept. The region I will reject and the region I will fail to reject, because you don't ever get to accept the null hypothesis. You just either reject the null hypothesis or fail to reject that null hypothesis. But depending on what that significance level is going to be, what you're going to allow it to be off and still be okay, will create my critical regions. So if we look at some of our pictures that we have, just to kind of talk about what those critical regions look like. So if I look at page 398, on page 398, when I'm trying to say I'm allowing it to be an alpha of 0.05. So if my significance level is going to be at that 95% significance, so I'm allowing it to have 5% that it's off, then those z-scores that just cut off that top 5%, well, the z-score that gives me 5% at the top, so 95% to the left, is that 1.645. So anything that gives me a z-score more extreme than 1.645 is in my rejection region. Because if I'm assuming that I know that the population proportion is whatever, in this case it's 0.5, if I assume that I know that, and I get something that's way out here with a z-score beyond 1.645, then that's so far off with such a small probability of happening by chance that I need to say I'm going to assume my original assumption that the proportion equaled 0.5 had to be wrong. And this one's dealing with just a one-tailed test. This is when I'm claiming things are going to be greater than a value, and I will just look at this top right tail. If, on the other hand, I'm saying that the proportion does not equal, so my original claim had that it was equal to something, my null hypothesis was that it was equal, my alternative was not equal. When it's doing a not equal, I'll end up doing a two-tailed test. Because we have either option of, if I'm claiming that it was equal, then if it was either one of these other two extremes, then that would be in my rejection region. And so you have to take what your significance level, that 0.05, and we're going to cut that in half. And so I would say, well, that means 0.025 is in the bottom tail and 0.025 is in the top tail. And if it's in either one of these two extremes, so if it's beyond 1.96 or less than negative 1.96, if I get a z-score, a test statistic that's in either one of those two regions, that's my rejection region. Anything that's in the green, greenish blue, whatever color you want to call that, that's in my fail to reject region. Just because I get it in this green doesn't mean that my original statement had to be right. It just means it wasn't so far wrong that I have to throw it out. So if I'm claiming that the proportion of girls is 60%, and I'm getting something that, comes out over here, my 60% is not bad enough that I have to throw it out as being a bad answer. The proportion might actually be like 65% or 70%. And so I'm still close, but not quite right, is what that's telling me. Versus if I'm way out here in the extreme, and I've claimed that it was 60%, and I'm out here in the red region, then that means I'm so far off that I'm wrong, that I have to reject my null hypothesis that it really equaled 60% and it's something different. If I'm doing a left-tailed test, then you're trying to find that critical region is going to be in your left tail. And so you're going to put all, in this case, against keeping that significance level of 0.05, all 5% is in that bottom tail, where we get those z-scores of negative 1.645. If I'm doing that it's greater than, then we're doing just a right-tailed test, and all 5% is in that top right tail. So depending on if you have a two-tailed, a left-tailed, or a right-tailed test, depends upon where that critical region will be at. If it's in both sides, just the left side, or just the right side. And that is a huge piece to pay attention to as we go. Where is that critical region, and where are those z-scores that give me my critical values? And we'll compare where our critical values are to where our test statistics are. So this chapter is like pulling together several different things that we've talked about, all into one piece of information that is a very applicable type of thing. It will tell you what your significance level is. And from your significance level, you find your test statistics and your critical values. All right, so our significance level, denoted by alpha, is the probability that that test statistic will fall in the critical region when the null hypothesis is actually true. This is the same alpha that we talked about in section 7.2. So in chapter 7, when we talked about being 95% confidence, we had the alpha being the 5%. Same kind of thing here. We're looking at that alpha being the same kind of value. Common choices, again, for alpha are the 5%, the 1%, and the 10%. Truly what alpha is the probability of making the mistake of rejecting the null hypothesis when it is actually true. So you may have a case, we may have a case where 60% of NCMC students are females. But we could actually have a simple random sample, and we might come up with 40 out of the 50 being male. That will probably give us a case where we will throw that out of rejecting our null hypothesis. Even though it was really true, we would come out with something in that 5% region. We'd be out there in those tails, and we would reject it, even though the original was true. Because there is that chance that we could just get a sample and be a perfectly good sample that we're just off that far. But the likelihood of it is very small. And so it's one of those that alpha is just telling me the probability of actually making that mistake of rejecting that null hypothesis when it's actually true. And that one's called, I'm pretty sure that's the type 1 error. I won't worry about making you guys learn the types of errors. Questions on what that's telling us? So your critical value is any value that separates the critical region where we reject the null hypothesis from the values of the test statistic that do not lead to rejection of the null hypothesis. The critical values depend on the nature of the null hypothesis, the sampling distribution that applies, and the significance level alpha. So what that's telling us on these, each of these I was just using the z-scores. So that z distribution, we're using the normal distribution on these. Alpha was staying at 5% for all three of these. The nature of the null hypothesis and the alternative being the fact of, is it going to be equal to where I do the two tails? Is it a less than where I do a left tail? Or is it a greater than where I do a right tail? Depends upon what that critical value was. So in the top one, the critical values were the positive and negative 1.96. In the second one, the critical value was the negative 1.645. And the last one, the critical value was the positive 1.645. So each of those were those critical values separating the rejection region from the fail to reject region. Questions there? So our types of tests, and this is going to sound familiar because these are what I keep pointing to. Types of hypothesis tests can be a two-tailed, left-tailed, or right-tailed. The tails in a distribution are the extreme regions bounded by our critical values. If I'm doing a two-tailed test comes when my null hypothesis is equal. Now, obviously, as you're writing this, you have to have what your test statistic is, or your population parameter is. Is this a proportion, a mean, or a standard deviation? And you have to have your values. But your two tails come when your null is equal and your alternative is not equal. So this comes when I claim that the proportion equals or the mean equals a certain value. If that's the case, because that's going to be not equal, it can be in either one of the two. If it's too small or if it's too big, it's going to be a throw that possibility out. And so this is when I get my two tails. My fail to reject region's in the middle. I reject it if it's too small. I reject it if it's too big. And I have to figure out what that what that critical value would be. And when we're looking at this, whatever alpha is, it gets split into both of these tails. And so you have to cut alpha in half to figure out what it is in both tails. And so when you're dealing with that two-tailed, so alpha is divided equally between the two tails of your critical region. So when you're doing a not equal, you're doing a two-tailed test, alpha gets split in half. On the other hand, if instead of being not equal, if I'm doing it being less than, so my alternative says it's less than points left, therefore it's going to have on the left side is where I will find my critical region. So this critical region, all of alpha is going to be in this left tail. And I will find what that critical value is that separates that alpha being to the left of it from the rest of it to the right of it. And so my rejection region would just be in the left side. So alpha is all in the left tail when I do that. Questions there? Compared to my right tail is when it's going to be greater than. Greater than points to the right, therefore the greater than is a right-tailed test. So my rejection region is just in the right tail. My fail to reject is in the left tail. So all of alpha is going to be in the right tail when I'm looking at this one. Questions there? Draw your pictures when you do these. Find your critical values. Write those down because it'll help you keep track of what you're doing. So drawing just your little distribution, figuring out, am I doing a two-tailed, a one-tailed, a left-tailed, a right-tailed? What am I dealing with as you do these? We'll find the calculations for the p-value and what to do with that next time. Do I want to give you homework? Just giving you some start on this. You know, I think I'm just going to wait. Don't forget also, registration begins April 2nd. Our test will be on April 15th. If you haven't done course evaluations, please do your course evaluations. That is that whole, you guys get to decide if you do this or not. So it's not a good sampling technique, but that doesn't mean my administration doesn't look at it. So if I could get everybody to do it, then I would have a good sample that we could look at, have the entire population, and we could really look at whether I'm doing a good job of teaching or not. Also, we don't get to see those until after we turn in grades, so it can't hurt your grades.